Okay, I'll be doing a series of videos about power series as far as we use them to solve differential equations. This is obviously not everything there is to know about power series, but this will get us through what we need to do for our differential equations class. So, first issue, what is a power series? It looks like that, and we might say in this case that it's a sub n, which is some generic constant, times x minus a to the n power, that this is a power series centered at x is equal to a. And what you'll notice about it is if you run this summation, you get a constant term, and then you get a term that has an order of the first power on the x, and then an order of the second power, and the third power, and you know how it goes from there. Okay, so that's what a power series is. All these a sub 0, a sub 1, a sub 2, those are all constants, which all might be different. All right. So here's an easy example. That right there would be a power series. Let's have a look at it. Say we just wrote some of it out to explore it. I would find that the first term was 1, and then the second term was, maybe we could say 1/2 x, because I did make the claim that this deal is going to be a constant, a coefficient, times x to some power, right? And then I'll get 1/3 x squared, and then I'll get 1/4 x to the third power, and you get the idea. So that's what this one would be. Now, a power series is an infinite series, and what we could wonder about any infinite series is, does the series converge? Meaning, if you were to add and add and add, would your partial sums get closer and closer to something? It turns out if we go back to what you're supposed to learn in calculus 2, we can find that the interval of convergence for that power series right there is anything between -1 and 1, and including the -1. Those numbers going for the x, make any choice in here, you'll get an infinite series that converges. Okay, so that's one basic example of a power series. That will give you something to think about when we see other more generic power series in the future. Okay, so the next thing that would pertain to our class is this thing called the coefficient theorem for power series. Have a look what it says. It says, if I have a power series and it's equal to 0, then every coefficient is also 0. Okay? Wouldn't matter what form the power series take, it's going to be a constant term plus a constant times x minus a to the first power, and so on. Well, every single coefficient right there has got to be 0 if this is where you start. Okay? All right, now, so this is something that we'll have to get good at recognizing. Take this one right here. Suppose I give you that statement or that equation, which seems to involve a power series. What can you tell me about the coefficients? All right, well, first thing I'd recognize is this, as it's given right there, is not really in that form. It needs some rearranging, okay? So how about this? Let's write out some of those terms and figure out how we can configure this whole thing so that that applies to it. All right? So here's the equation in its new form. I get a sub 0 being my first term of that series, which would be a constant. I get a1 x. Okay, and then I get a2 x squared. And then it strikes me that what I need to do is combine like terms in order to express all this as a power series, as one power series. and then appeal to that. Okay, so how about this? You get that, and where do we pick up from here? Well, we went to order 2, so we need to say 3 to infinity, an xn, and then plus these things. All right, now I see that there's lots of like terms right there. Let's put things in order. You know, the way they would be if we just had one summation to represent our power series. Let's put them in order. I get a constant term, okay? And then 4x and a1x. Okay, so let's say 4 plus a1x. Okay, and that's my term that has an order of the first power. And then x squared. All right, so let's say a2 plus the coefficient there is 1, and that's x squared. Okay, so I gathered all that together, and now I see a power series. Here's the constant term, x to the first power, x to the second power. Where would this pick up? That would pick up from x to the third power. So it picks up exactly where it needs to be for this to be one term by term power series. Okay, now there you have it. That is just this. And so what's every coefficient supposed to be? The coefficient of every term through that whole thing has got to be 0. So here's what we say about it. We say that, what would be the a sub 0 term there? The constant term, the very first thing out of this, that's got to be 0. Okay, and what about this one? Okay, the order x term. Well, 4 plus a1 has got to be 0. So let's say we know that a1 has got to be -4. Okay, what about a2? Well, remember, in this power series right there, every term accounted for, all coefficients have to be 0. So a2 has got to be -1. And then what are we going to say about the others? Well, all the others are here, and they're going to have to be 0. So let's just say an would have to be 0 for, and let's just say, instead of write them all out, we'll say, whoops. Let's just say 4 n greater than or equal to 3. So 3, 4, 5, and so on. All right? Okay. So there's my answer. That's my statement about what the coefficients have to be right there. Okay? Now let's consider a different question. Say I give you something like that, all right, which has only one summation and one formula. What are the coefficients going to be there? Okay, so I note that this one is a more typical power series the way it's given. You know, even though that looks more complicated, it's really just something that's like that. If we go look at the one down there, there'll be a constant term, and x to the first power, x to the second power. It's all going to be there. Check it out. So put 0 in, that erases the x, and then you'll get some constant in there. You know, a sub n plus 2, those are all constants. Okay, who knows what it is, but you'll get a constant. Then you'll get an x. Then you'll get an x squared. So, well, there's your coefficient of every single term. So I could immediately say that here's what's got to happen. N plus 2, n plus 1, a n plus 2 plus a n has got to be 0. Okay? And let's reduce that and just end up, let's solve for like the later coefficient in terms of the earlier. And if we do that, we'll get a n plus 2. The number that's actually an index of 2 ahead of that one, that's got to be negative a n over n plus 2 times n plus 1. And what's this true for? Well, it'd be true for however you're counting through the series. So let's put 4 n greater than or equal to 0. So of course 0, 1, 2, 3, and on. Okay. Now it might be that in a case like this, that all of the coefficients aren't different. It might be that we can find the later ones in terms of the earlier ones. So like here's what we'll notice. Let's go ahead and go through this and look at the possibilities. Say you put 0 for n, because that's the first number you're allowed. It would say a sub 2 is negative a naught over 2. So let's say that. You know, apparently you find term a2 in terms of a naught. Okay, and what's a sub 3? Okay, so in order to find that, we would put 1 in and find this negative a1 right away over 6. Okay, and what's a 4? Well, you see how I'm using that by now. So it's going to be negative a2. All right. That's what I get. Over 4 times 3, so over 12. But it would really be my goal when I solve these to find all coefficients in terms of like the first two. So maybe I'll find everything in terms of a naught and a1. Okay. All right. So in this case, I don't know a naught. It might be some undetermined constant in our problem, but I can find a2 if I had it. And same with a1. I may not know what that is, but I can find a sub 3 in terms of it if I had it. How would you find the constants in your general solution? In a differential equation, well, you would use initial conditions if you had them. So that's what those turn out to be. Anyway, so what do we say about a4? But I know what a2 is. You know, so if I initially get this, I will make use of that. a2 is negative a naught over 2. So we're going to say positive a naught over 24. Okay? And I'll just have to put a big etc., right? You get it. You can keep going. You use this the way it's given to you. If you can, through back substitution, find your new term in terms of the earlier ones, then we do that. I promise if you keep going in this, you'll find everything in terms of a naught and a1. All right? Okay, so the question was, what are the coefficients? Well, I can't tell you number for number what they are, but I can tell you that this is how they're related, and that's what I'd want to do.